Is there another Earth? The intriguing question of another Earth. Look up at the night sky, and you'll see countless stars, each one a tiny beacon in the vast expanse of the universe. But have you ever wondered if, orbiting one of those stars, there's a planet just like ours? Could there be another Earth out there, waiting for us to discover it, a world with oceans, mountains, and perhaps even life? This question has captivated humanity for generations, driving our imagination and fueling one of the most ambitious scientific quests in history, the search for habitable exoplanets. The idea of finding another Earth isn't just a fantasy for dreamers or science fiction enthusiasts. It's a question that challenges our understanding of life, our place in the cosmos, and the possibilities for humanity's future. Is Earth truly unique, or is it one of many life-sustaining planets scattered across the universe? And if such a planet exists, what might it mean for us? Why the search for a second home matters. The search for a second Earth is no longer a matter of curiosity, it's a necessity. With Earth's ecosystems under pressure from climate change, resource depletion, and overpopulation, scientists are exploring the possibility that our survival might one day depend on finding a new home. Rising sea levels, extreme weather, and dwindling natural resources are more than just environmental challenges. They're signals that our planet's capacity to support life as we know it may not last forever. But beyond the practical necessity lies an even greater purpose: the quest for knowledge. Discovering another Earth-like planet wouldn't just offer an escape plan. It would answer one of humanity's most profound questions: are we alone? The possibility of finding another habitable world brings hope, but it also raises challenging questions about what it means to live beyond the boundaries of our own planet. The search for exoplanets begins in the last few decades. The discovery of exoplanets, planets that orbit stars outside our solar system, has transformed our understanding of the universe. These distant worlds have gone from being theoretical concepts to proven realities, thanks to groundbreaking advancements in space exploration. Since the first exoplanet was confirmed in the 1990s, scientists have identified over 5,500 exoplanets, and the number continues to grow as our tools for detection become more sophisticated. Among these discoveries, the search for planets in the Goldilocks zone has taken center stage. This is the region around a star where conditions might be just right for liquid water, a key ingredient for life to exist. Earth resides in the Sun's Goldilocks zone, and scientists believe that finding similar conditions elsewhere could unlock the potential for habitable planets. Our tools for exploration, like the Kepler Space Telescope, TESS, and the powerful James Webb Space Telescope, have revolutionized our ability to study these distant worlds. With each discovery, we move closer to answering the ultimate question: could there be another Earth out there, hidden among the stars? This journey into the unknown is more than just a scientific endeavor. It's a story of human curiosity, resilience, and ambition. The quest to find another Earth challenges us to look beyond the boundaries of our solar system, inspiring new questions about life, technology, and what it means to explore the universe. Let's embark on this fascinating journey and uncover the secrets of the stars, where the answers to humanity's greatest questions may lie waiting. What are exoplanets? Understanding exoplanets and their unique nature. Exoplanets are planets that orbit stars outside our solar system, a term that didn't enter scientific discussions until relatively recently. Unlike the familiar planets of our solar system, Mercury, Venus, Mars, and so on, these worlds are scattered across the galaxy, orbiting stars that are sometimes similar to our Sun and, in other cases, vastly different. What makes exoplanets so fascinating is their sheer diversity and the potential they hold for expanding our understanding of what planets can be and how life might exist in the universe. In many ways, exoplanets challenge our preconceived notions about planetary systems. For decades, we assumed most planetary systems would look like ours, with small rocky planets close to the star and gas giants further away. But discoveries have proven that the universe is full of surprises. There are exoplanets so close to their stars that their surfaces are molten, and others so far away that they're locked in eternal ice. Some orbit not one but two stars, creating a cosmic dance reminiscent of science fiction landscapes. Each discovery adds a new layer to the complex puzzle of planetary formation and evolution, reshaping how we think about our place in the cosmos. The diverse types of exoplanets. Exoplanets come in a dizzying variety of types, ranging from enormous gas giants to small rocky worlds. Among them are gas giants like Jupiter and Saturn, but with far more extreme characteristics. For example, some of these gas giants, called hot Jupiters, orbit so close to their stars that their atmospheres are constantly being stripped away by stellar winds. Their temperatures can soar to thousands of degrees, making them some of the most hostile places imaginable. Then there are ice planets, which are often found in the colder, outer reaches of their star systems. These planets resemble Neptune or Uranus but may also harbor icy surfaces or subsurface oceans, potentially making them intriguing candidates for further study. While their icy conditions might seem inhospitable at first glance, some scientists speculate that under the right circumstances, even these frozen worlds could host microbial life. The most compelling category, however, is rocky planets, which are similar in composition to Earth. These planets are primarily made of silicate rocks and metals, and their solid surfaces make them the most promising candidates for habitability. Scientists are particularly interested in rocky exoplanets that fall within the size range of Earth, referred to as super-Earths, when they are slightly larger. These planets, especially if located in the habitable zone of their stars, provide the best chance of finding a world that could sustain life. The significance of the Goldilocks zone. For any planet to be considered potentially habitable, its location relative to its star is critical. Enter the concept of the Goldilocks zone, named for its conditions being just right. This is the orbital region around a star where a planet could maintain temperatures suitable for liquid water to exist on its surface, a key ingredient for life as we know it. The Goldilocks zone isn't a fixed distance. It varies depending on the star's size and energy output. For example, smaller, cooler stars like red dwarfs have their habitable zones much closer in, while larger, hotter stars have habitable zones farther away. But location alone isn't enough. The planet must also have the right atmospheric conditions to retain liquid water and regulate its temperature. Without an atmosphere, even a planet in the perfect orbital position would become a lifeless rock or an icy wasteland. One of the most famous examples of a star system with multiple planets in the habitable zone is TRAPPIST-1. This red dwarf star hosts 7 rocky planets, 3 of which lie in the Goldilocks zone. The discovery of this system was groundbreaking, as it demonstrated that habitable zones are not unique to our solar system and that rocky planets with potential for water could exist in abundance. The growing list of known exoplanets. Since the first exoplanet was confirmed in 1992, the field of exoplanet research has exploded. Today, astronomers have identified over 5,500 exoplanets, with more being discovered every year. This number represents only a fraction of the potential planets in our galaxy, as current technology limits our ability to detect smaller, more distant worlds. It's estimated that the Milky Way alone could host hundreds of billions of exoplanets. Of the known exoplanets, around 50 are considered potentially habitable based on their size, composition, and location within their star's habitable zone. Each of these worlds represents a tantalizing possibility: a new Earth, a place where life might exist, or where humanity could someday thrive. With missions like TESS and the James Webb Space Telescope pushing the boundaries of what we can observe, the list of known exoplanets continues to grow, and with it, the hope of finding another Earth. Expanding our understanding of the cosmos, the study of exoplanets has reshaped our understanding of the universe, revealing its incredible diversity and vast potential. These discoveries not only bring us closer to answering whether life exists elsewhere but also deepen our appreciation for the unique conditions that make Earth so special. As scientists uncover more about these distant worlds, they're opening a new chapter in the story of human exploration, a journey that begins with the simple, yet profound, question: is there another Earth out there, waiting for us to find it? How we discover exoplanets. It's the science behind exoplanet detection. And the discovery of exoplanets is one of the most groundbreaking achievements in modern astronomy, offering humanity a glimpse into the vast diversity of worlds beyond our solar system. But finding these distant planets is no small feat. Unlike the planets in our solar system, exoplanets are incredibly faint and often hidden by the brightness of the stars they orbit. Detecting them requires sophisticated techniques and cutting-edge technology, pushing the boundaries of human ingenuity. Over the past few decades, astronomers have developed several methods to identify and study these distant worlds, each offering unique insights into their properties and potential habitability. The transit method, dimming stars reveal hidden planets. The most widely used technique for discovering exoplanets is the transit method, a process that relies on detecting the tiny dip in a star's brightness when a planet passes, or transits, in front of it. Imagine a small moth flying in front of a flashlight beam. While the light may still shine brightly, there's a momentary dimming. This is essentially what astronomers observe when an exoplanet crosses its star. The transit method has been remarkably effective because it not only confirms the presence of a planet but also reveals valuable information about its size, orbit, and even its atmosphere. When a planet transits its star, some of the starlight passes through the planet's atmosphere, allowing scientists to analyze the light using a technique called spectroscopy. By studying how the light is absorbed or scattered, researchers can identify the chemical composition of the atmosphere, searching for key markers like water vapor, carbon dioxide, or even oxygen, potential indicators of habitability. This method works best with stars that are relatively small and dim, such as red dwarfs, as the contrast between the star and the planet is more pronounced. One of the most famous discoveries using the transit method is the TRAPPIST-1 system, where 7 Earth-sized planets were identified, 3 of which lie in the habitable zone. The radial velocity method, detecting stellar wobbles, while the transit method measures light, the radial velocity method focuses on motion. When a planet orbits a star, its gravitational pull causes the star to wobble slightly in its position. This wobble is minuscule but measurable, thanks to the Doppler effect, a phenomenon where the star's light shifts slightly toward the red or blue end of the spectrum, depending on whether it's moving away from or toward Earth. By analyzing these shifts, astronomers can determine not only the presence of a planet but also its mass and orbital period. The radial velocity method was responsible for the discovery of the first confirmed exoplanet, 51 Pegasi b, in 1995. This groundbreaking discovery earned its discoverers the Nobel Prize in Physics and opened the floodgates for a new era of exoplanet research. Although this technique is highly effective, it works best for detecting massive planets like gas giants, which exert a stronger gravitational pull on their stars. However, advancements in technology are making it increasingly possible to use this method for identifying smaller, Earth-like planets as well. Direct imaging, capturing the unseen. While most exoplanets are discovered indirectly, there are rare cases where telescopes can directly capture images of these distant worlds. Direct imaging involves blocking out the overwhelming light of a star to reveal the faint glow of orbiting planets. This is achieved using devices like coronagraphs and starshades, which act as sunglasses for telescopes. Direct imaging is particularly useful for studying planets that are far from their stars, as these planets reflect less starlight and are easier to isolate. It also provides critical data about a planet's surface and atmospheric properties, offering a closer look at its potential for habitability. One of the most famous examples of direct imaging is the Hour 8799 system, where astronomers captured images of 4 massive planets orbiting their host star. These observations not only confirmed the existence of these planets but also allowed scientists to analyze their atmospheres in unprecedented detail. Although direct imaging remains challenging and is limited to a small number of cases, it represents a promising frontier in the search for exoplanets, especially as telescope technology continues to improve. Kepler and TESS, revolutionizing exoplanet discovery. The search for exoplanets took a quantum leap with the launch of the Kepler Space Telescope in 2009. Kepler was specifically designed to use the transit method, monitoring over 150,000 stars for tiny dips in brightness that could indicate orbiting planets. Over its 9-year mission, Kepler discovered more than 2,600 confirmed exoplanets, including a significant number of Earth-sized planets in habitable zones. Its findings fundamentally changed our understanding of planetary systems, revealing that planets are far more common than previously thought. Following Kepler's success, NASA launched the Transient's Exoplanet Survey Satellite, TESS, in 2018. TESS expanded on Kepler's mission, focusing on stars closer to Earth and brighter, making it easier to study the planets it discovered. With TESS, scientists have identified dozens of promising candidates for further study, including TOI 700d, an Earth-sized planet in its star's habitable zone. These space telescopes have not only increased the number of known exoplanets but also laid the groundwork for future missions. By identifying promising targets, they've paved the way for more advanced telescopes to study these worlds in greater detail. Breakthroughs in technology, a new era of exploration. And the next chapter in exoplanet discovery is being written with cutting-edge technology, led by the James Webb Space Telescope, JWST. Launched in 2021, JWST is equipped with powerful infrared instruments capable of analyzing the atmospheres of distant planets. Its ability to detect faint signals and study light from exoplanets with unprecedented precision has already yielded groundbreaking insights. For example, JWST recently observed the atmosphere of WASP 96b, a gas giant over 1,000 light-years away, detecting the presence of water vapor, clouds, and haze. Such detailed observations mark a significant step forward in understanding the conditions on exoplanets and searching for biosignatures, chemical markers of life. In addition to JWST, advancements in spectrometry are revolutionizing how scientists study exoplanet atmospheres. High-resolution spectrometers can now detect subtle variations in light, allowing researchers to identify specific molecules, like methane or carbon dioxide, that could indicate biological activity. Future missions, such as the European Space Agency's Plato and NASA's Nancy Grace Roman Space Telescope, promise to push the boundaries even further. These missions aim to study a broader range of stars and planets, offering new insights into planetary formation, composition, and habitability. A continuous journey of discovery. The quest to discover exoplanets is a testament to humanity's ability to push the limits of what's possible. From detecting tiny dips in starlight to capturing direct images of alien worlds, each method contributes to a deeper understanding of our place in the universe. The combination of innovative techniques and groundbreaking technologies has transformed what was once a distant dream into a rapidly expanding field of study. With thousands of exoplanets already identified and countless more waiting to be discovered, the search for another Earth is more exciting than ever. Each discovery brings us closer to answering profound questions about the nature of life, the diversity of worlds, and the future of humanity in the cosmos. The tools we've built, and those still to come, are lighting the way toward new horizons, where the secrets of distant planets are waiting to be unveiled. What makes a planet habitable? The key ingredients for habitability. When scientists search for habitable exoplanets, they're not just looking for planets that resemble Earth in size or appearance. They're looking for worlds that meet specific criteria, conditions that we know are essential for life as we understand it. These conditions are based on what we've learned from our own planet, Earth, which serves as the ultimate benchmark for habitability. One of the most important criteria is the presence of liquid water. Water is essential for all known forms of life, serving as a medium for biochemical reactions and a transport system for nutrients and waste. For water to remain liquid, a planet must have the right temperature range, which is why the concept of the Goldilocks zone is so critical. This is the zone around a star where temperatures are just right for liquid water to exist, not too hot, not too cold. But water alone isn't enough. A planet must also have a stable atmosphere to regulate temperature and protect life from harmful space radiation. Without an atmosphere, water would evaporate or freeze, and extreme temperature fluctuations could make life impossible. Another crucial factor is a magnetic field, which shields a planet from cosmic and solar radiation. Earth's magnetic field is generated by the movement of molten iron in its core, creating a protective bubble that deflects charged particles from the Sun. Without this magnetic field, our atmosphere would have been stripped away over billions of years, leaving the surface exposed to deadly levels of radiation. Mars, for example, lacks a significant magnetic field, which is one reason why it's a cold, barren desert despite being in the Sun's habitable zone. Earth, the gold standard of habitability. The Earth is the only planet we know of that supports life, and its unique combination of factors makes it an ideal benchmark for habitability. Our planet's position in the Sun's habitable zone allows for liquid water to exist on its surface, creating oceans that cover more than 70% of the planet. These oceans play a vital role in regulating temperature, driving weather patterns, and supporting a diverse range of life forms. Earth's atmosphere is another critical factor. Composed primarily of nitrogen and oxygen, it acts as a blanket that traps heat, keeping temperatures within a range suitable for life. The atmosphere also filters out harmful ultraviolet radiation through the ozone layer and allows for a stable climate that has persisted for billions of years. Additionally, Earth's magnetic field provides a robust shield against solar winds, protecting the atmosphere and allowing life to thrive on the surface. The planet's plate tectonics also play a role in recycling carbon dioxide, which helps regulate the greenhouse effect and maintain a stable climate. Earth's biodiversity further underscores its habitability. Life has evolved to fill every ecological niche, from the depths of the oceans to the peaks of mountains, showcasing the incredible adaptability of living organisms. This adaptability has led scientists to question whether life might exist in environments vastly different from those found on Earth. Life in extreme environments, expanding the definition of habitability. One of the most surprising discoveries in recent decades is the resilience of life in extreme environments on Earth. Organisms known as extremophiles have been found thriving in conditions once thought to be inhospitable. These findings have broadened our understanding of where life could potentially exist, even beyond Earth. Take, for example, the deep ocean vents where hydrothermal activity releases scalding water rich in minerals. Despite the high pressure, absence of sunlight, and extreme temperatures, these vents are teeming with life. Microorganisms here rely on chemosynthesis, a process that uses chemical energy, rather than sunlight, to produce food. Similarly, in Antarctica, microorganisms have been found living in subglacial lakes, surviving on the limited nutrients available in total darkness and extreme cold. Even highly acidic environments, such as those in volcanic hot springs, and highly saline conditions, like salt flats, have been found to support life. These discoveries suggest that life might not require Earth-like conditions to thrive. If extremophiles can survive in such harsh conditions here, could similar life forms exist on exoplanets with extreme environments? Challenging assumptions, life beyond Earth-like conditions. The search for habitable planets often focuses on finding Earth analogues, worlds with similar sizes, atmospheres, and conditions. But what if life could exist in environments completely different from our own? This idea has sparked debates among scientists, challenging traditional assumptions about habitability. One of the most intriguing possibilities is the existence of methane-based life. On Earth, water serves as the solvent for biochemical reactions, but methane could potentially play a similar role on colder worlds. Titan, Saturn's largest moon, offers an example of this possibility. Titan has rivers, lakes, and seas of liquid methane and ethane, with a thick atmosphere that could support exotic forms of life. While methane-based life forms would operate on entirely different biochemistry, they might still thrive in conditions that mimic Earth's, only with methane instead of water. Another controversial insight is the idea that life might not require a planet at all. Some scientists speculate that life could exist on rogue planets, worlds that have been ejected from their star systems and float through space. While these planets lack the energy of a nearby star, internal heat from radioactive decay or tidal forces could provide enough warmth to sustain subsurface oceans. This challenges the notion that habitability is tied to a star's habitable zone. The concept of panspermia further complicates the picture. This theory suggests that life could be transported between planets or even star systems by meteoroids or comets, potentially seeding life on worlds that lack the conditions for its independent emergence. If true, this could mean that life isn't confined to any particular type of planet or environment. It could adapt and thrive wherever it lands. The expanding horizon of habitability. As we continue to explore the universe, our understanding of what makes a planet habitable is constantly evolving. While Earth remains the gold standard, discoveries on our own planet and elsewhere in the solar system are challenging the boundaries of habitability. From extremophiles in Earth's harshest environments to the possibility of methane-based life on Titan, each new finding expands the horizon of what we consider possible. This growing understanding fuels the search for exoplanets, encouraging scientists to look beyond Earth-like worlds and consider the full spectrum of planetary conditions. With advancements in technology and new missions on the horizon, the next decade promises to reveal even more about the incredible diversity of planets and the potential for life beyond our solar system. Whether life thrives on rocky worlds like Earth, icy moons, or methane-rich planets, the search for habitability is ultimately a search for answers about our place in the cosmos. Could life as we know it, or as we've yet to imagine it, exist among the stars? The quest continues, driven by the hope that somewhere, out there, another habitable world awaits. Case studies, the most promising exoplanets Proxima b, a neighbor with potential and challenges. Proxima b is one of the most exciting discoveries in the search for habitable exoplanets. Orbiting Proxima Centauri, the closest star to our solar system, this planet lies a mere 4.24 light-years away, a cosmic stone's throw compared to most exoplanets. Proxima b orbits within its star's habitable zone, where temperatures might allow for liquid water to exist. This rocky planet is slightly larger than Earth, with a mass about 1.3 times that of our planet. Proxima Centauri is a red dwarf star, significantly smaller and cooler than our Sun. This allows Proxima b to orbit much closer to its star, about 20 times closer than Earth is to the Sun, while still remaining in the habitable zone. However, this proximity comes with a significant downside: stellar flares. Proxima Centauri is highly active, emitting intense bursts of radiation that could strip away Proxima b's atmosphere over time. Without an atmosphere to regulate temperature and shield the surface, the planet's ability to sustain life would be severely compromised. Despite these challenges, Proxima b remains a compelling candidate for habitability. Some theoretical models suggest that a sufficiently strong magnetic field or a thick atmosphere could protect the planet from its star's radiation. With advancements in telescopic technology, future studies may determine whether Proxima b's conditions truly support life or if its potential remains out of reach. Kepler 452b, Earth's older cousin. Kepler 452b, often referred to as Earth's older cousin, has captured the imagination of scientists and the public alike. Discovered by NASA's Kepler Space Telescope, this exoplanet orbits a star remarkably similar to our Sun, but older by about 1.5 billion years. Kepler 452b is located approximately 1,400 light-years away in the constellation Cygnus. This rocky world is about 60% larger than Earth, placing it in the category of super-Earths. It resides firmly within its star's habitable zone, where surface temperatures could support liquid water. However, its size and age present both opportunities and challenges. Being larger than Earth, Kepler 452b likely has stronger gravity, which could affect the planet's atmosphere and surface conditions. Additionally, its star's advanced age raises questions about the planet's ability to retain an atmosphere over billions of years of exposure to solar radiation. Kepler 452b's significance lies in its similarities to Earth and its location in a stable habitable zone. While its distance makes it difficult to study in detail, it serves as a powerful reminder that Earth-like planets may not be as rare as once thought. Scientists continue to model its atmospheric and geological characteristics to explore its potential for hosting life. TRAPPIST-1 system, a treasure trove of Earth-sized world. The TRAPPIST-1 system is one of the most remarkable discoveries in exoplanet science, featuring not one but 7 Earth-sized planets orbiting a single star. Located about 39 light-years away in the constellation Aquarius, TRAPPIST-1 is a red dwarf star, much smaller and cooler than the Sun. Its planets orbit extremely close to the star, but because of the star's low energy output, 3 of them, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1 fall within the habitable zone. These planets are tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. This creates a unique environment where habitable conditions might exist only in the terminator zone, the thin region between the day and night sides. Theoretical models suggest that these planets could have atmospheres capable of distributing heat, potentially making them more hospitable than the tidal locking might suggest. TRAPPIST-1's planets have drawn intense interest because of their potential for comparative study. With 7 planets in one system, astronomers can explore how different factors, such as distance from the star or atmospheric composition, affect habitability. The James Webb Space Telescope has already begun studying this system, searching for atmospheric biosignatures that could indicate the presence of life. LHS 1140b, a super-Earth with a dense atmosphere. LHS 1140b is a super-Earth that has quickly become one of the most promising candidates for habitability. Discovered in 2017, this rocky planet orbits a red dwarf star about 49 light-years away in the constellation Cetus. With a mass nearly 7 times that of Earth, LHS 1140b is larger and denser than our planet, suggesting it has a substantial rocky core. What makes LHS 1140b particularly intriguing is its location within its star's habitable zone and the potential for a dense atmosphere. The planet's higher gravity could help it retain an atmosphere despite the star's radiation. Additionally, its orbit brings it close enough to the star to receive adequate energy for liquid water to exist, but not so close as to experience extreme heat or radiation. Recent studies using spectroscopic techniques suggest that LHS 1140b may have a water-rich atmosphere, though confirmation is still pending. If these findings are verified, LHS 1140b could provide an invaluable opportunity to study the conditions necessary for life on larger, rocky planets. TOI 700d, a new hope in the habitable zone. TOI 700d is one of the newest additions to the list of potentially habitable exoplanets. Discovered by NASA's Transients Exoplanet Survey Satellite, TESS, in 2020, this Earth-sized planet orbits a red dwarf star about 101 light-years away in the constellation Dorado. TOI 700d is the outermost of 3 planets in its system and the only one within the star's habitable zone. With a size and mass similar to Earth, TOI 700d is an exciting target for further study. Its location in the habitable zone suggests that surface temperatures could support liquid water, making it a strong candidate for life. Additionally, the planet's relatively stable star minimizes the risks associated with stellar flares, which are common in red dwarf systems. While TOI 700d's distance makes direct observation challenging, upcoming missions and telescopes are expected to provide more detailed insights. Simulations of its climate and atmosphere are already underway, helping scientists assess its potential as a habitable world. Key statistics and data, comparing promising exoplanets. The most promising exoplanets offer a fascinating glimpse into the diversity of potentially habitable worlds. For instance, Proxima b is only 4.24 light-years away, making it the nearest candidate, while Kepler 452b lies a distant 1,400 light-years away. TRAPPIST-1's planets are remarkable for their number and variety, with 3 located in the habitable zone of their system. LHS 1140b stands out for its dense atmosphere and rocky composition, while TOI 700d combines Earth-like size with a favorable location in its star's habitable zone. Surface temperatures vary widely among these planets, depending on their distance from their stars and atmospheric conditions. For example, TRAPPIST-1e is estimated to have temperatures similar to Earth's, while Proxima b's conditions depend heavily on whether it has a protective atmosphere. The diversity in these exoplanets highlights the need for continued study to better understand their potential for life. Theoretical models, simulating life on distant worlds. To assess the habitability of these exoplanets, scientists rely on theoretical models and computer simulations. These tools allow researchers to explore how factors like atmosphere, surface composition, and stellar radiation interact to create conditions suitable for life. For example, models of TRAPPIST-1's planets have shown that even with tidal locking, heat could be evenly distributed by atmospheric winds, potentially making these planets habitable. Simulations of Proxima b have explored scenarios in which a thick atmosphere or magnetic field protects the planet from stellar flares, increasing its chances of supporting life. Similarly, studies of LHS 1140b suggest that its high gravity could help retain a water-rich atmosphere, despite the challenges posed by its proximity to a red dwarf star. These models not only provide insights into the specific conditions of each planet, but also help refine the criteria for habitability. By testing different scenarios, scientists can identify the most promising targets for future exploration and guide the development of new technologies to study these distant worlds. A growing catalogue of possibilities. The discovery of these promising exoplanets represents a significant step forward in the search for another Earth. Each planet offers a unique set of conditions that expand our understanding of habitability, from Proxima b's proximity to TRAPPIST-1's diversity to Kepler 452b's similarities to our own world. With advancements in technology and ongoing missions like the James Webb Space Telescope, the coming years promise to unveil even more about these distant worlds and their potential to host life. As we continue to study these planets, we're not just learning about their individual characteristics, we're building a deeper understanding of the universe and our place within it. Each discovery brings us closer to answering one of humanity's most profound questions: are we alone? The search for habitable exoplanets is more than a scientific endeavor. It's a journey into the unknown, fueled by curiosity and the hope that somewhere, out there, another Earth awaits. The role of artificial intelligence in exoplanet hunting. AI in astronomy. A new era of exploration. Artificial intelligence has become a transformative force in the field of astronomy, reshaping how scientists explore the universe. One of its most significant contributions lies in the search for exoplanets, where AI has proven invaluable in processing the massive datasets generated by modern telescopes. These datasets are so vast and complex that traditional methods of analysis would take decades to sift through, yet AI can accomplish this task in a fraction of the time. Modern space telescopes, such as the Kepler Space Telescope and the Transient's Exoplanet Survey Satellite, TESS, collect immense amounts of data, monitoring thousands of stars simultaneously for subtle changes in brightness that might indicate the presence of an orbiting planet. This raw data often includes countless variations caused by noise, stellar activity, or even human interference. Identifying true planetary signals among these fluctuations is akin to finding a needle in a haystack, an overwhelming challenge for human astronomers. That's where AI steps in, using its ability to process and analyze massive datasets far more efficiently than any human ever could. AI algorithms are designed to detect patterns and anomalies in this data, enabling astronomers to pinpoint potential exoplanets quickly and accurately. This process not only speeds up discoveries but also reduces the likelihood of false positives, ensuring that resources are focused on the most promising candidates. By automating tasks that would otherwise require years of manual labor, AI allows researchers to dedicate their efforts to interpreting results and refining their search strategies, ultimately accelerating humanity's quest to find another Earth. Pattern recognition, identifying exoplanets faster than ever. The core strength of AI lies in its ability to recognize patterns, a skill that is particularly useful in exoplanet hunting. Machine learning, a subset of AI, involves training algorithms to recognize the unique signatures of exoplanets based on known examples. Once trained, these algorithms can analyze new data, flagging potential exoplanets for further study. For instance, when a planet transits in front of its star, it causes a temporary dip in the star's brightness. This is one of the most common methods for detecting exoplanets, but the variations in brightness are often incredibly subtle, buried within noisy datasets. AI-powered systems can analyze these light curves, identify patterns consistent with planetary transits, and distinguish them from other phenomena like star spots or binary star interactions. Machine learning models can also be trained to detect radial velocity shifts, another key method for identifying exoplanets. These shifts occur when the gravitational pull of a planet causes its host star to wobble slightly, leading to detectable changes in the star's light spectrum. By analyzing these shifts, AI can help identify exoplanets that would otherwise go unnoticed due to the complexity of the data. What makes AI particularly powerful is its ability to learn and improve over time. As more exoplanets are discovered, the algorithms become increasingly accurate, refining their ability to detect even the faintest signals. This iterative process ensures that AI systems are constantly evolving, staying ahead of the challenges posed by ever-growing datasets and the need for more precise measurements. Real-life examples. AI's impact on exoplanet discoveries. AI has already played a pivotal role in some of the most significant exoplanet discoveries to date. In 2018, researchers at NASA used a neural network, a type of machine learning algorithm, to reanalyze data from the Kepler Space Telescope. This led to the discovery of two previously overlooked exoplanets, Kepler 90I and Kepler 80G. These planets had been missed in earlier analyses due to the sheer volume of data, but the neural network was able to identify their faint signatures, demonstrating the potential of AI to uncover hidden worlds. Another breakthrough came with the discovery of TOI 700d, an Earth-sized planet in its star's habitable zone. AI algorithms were instrumental in analyzing data from TESS, confirming the planet's existence and its promising characteristics. This discovery marked a milestone in the search for habitable exoplanets, showcasing how AI can help identify planets with conditions similar to Earth's. Beyond individual discoveries, AI has also been used to analyze entire datasets, identifying trends and patterns that inform future missions. For example, AI has been employed to predict the likelihood of finding habitable planets in specific regions of the galaxy, guiding the focus of telescopes and other observational tools. This targeted approach increases the efficiency of exoplanet hunting, ensuring that resources are directed toward the most promising areas. AI's contributions extend beyond detection to the study of exoplanetary atmospheres. By analyzing spectroscopic data, AI can identify the chemical composition of exoplanet atmospheres, searching for biosignatures like oxygen or methane. This capability is critical for assessing the habitability of distant worlds and searching for signs of life beyond Earth. Future potential: the next frontier of AI in exoplanet hunting. The future of AI in exoplanet research is incredibly promising, with advancements poised to revolutionize the field even further. One of the most exciting prospects is the use of AI to identify smaller, Earth-like planets that are more difficult to detect. While current methods excel at finding larger planets, such as gas giants, Earth-sized planets often produce weaker signals that are easily lost in the noise. AI's ability to process and analyze faint signals with unprecedented precision could unlock the discovery of more Earth-like worlds. In addition to finding new planets, AI is expected to play a key role in characterizing their environments. Future telescopes, like the European Space Agency's Plato mission and NASA's Nancy Grace Roman Space Telescope, will generate massive datasets that require advanced AI algorithms to analyze. These tools will help determine the atmospheric composition, surface temperature, and potential for liquid water on newly discovered exoplanets, providing critical insights into their habitability. AI could also enhance our ability to study multi-planet systems, such as TRAPPIST-1. By analyzing the gravitational interactions between planets in these systems, AI can reveal details about their masses, orbits, and potential for stable climates. This information is essential for understanding the dynamics of planetary systems and their suitability for life. Looking even further ahead, AI may enable the discovery of rogue planets, worlds that drift through space without a host star. These planets are challenging to detect using traditional methods, but AI's pattern recognition capabilities could identify the subtle gravitational effects they exert on nearby objects. As space exploration expands, AI will likely be integrated into autonomous spacecraft and rovers, allowing them to analyze data in real time and make decisions without human intervention. This capability will be particularly valuable for missions to distant exoplanets, where communication delays make real-time decision-making impossible. AI is the key to unlocking the universe. Artificial intelligence has already transformed the search for exoplanets, and its potential for future discoveries is virtually limitless. By processing massive datasets, identifying patterns, and analyzing complex signals, AI has become an indispensable tool in humanity's quest to find another Earth. It has enabled the discovery of worlds that were once beyond our reach, provided insights into their environments, and guided the focus of future missions. The integration of AI into exoplanet research represents more than just a technological advancement, it's a paradigm shift in how we explore the universe. With each new discovery, AI brings us closer to answering some of humanity's most profound questions. Are we alone? Could life exist beyond Earth? And if so, where? As the capabilities of AI continue to evolve, so too will our understanding of the cosmos. The next generation of AI-driven tools promises to uncover worlds we can scarcely imagine, expanding the boundaries of human knowledge and opening new possibilities for exploration. In the search for exoplanets, AI is not just a tool, it's the key to unlocking the secrets of the universe. The search for biosignatures. What are biosignatures? In the quest to discover life beyond Earth, the search for biosignatures has become one of the most crucial endeavors. Biosignatures are measurable indicators of life, often in the form of chemical compounds or patterns that suggest biological activity. These signatures are considered the best evidence for the existence of life elsewhere in the universe, as they represent direct or indirect proof of ongoing or past biological processes. On Earth, life has left clear marks in the atmosphere, oceans, and soil, most notably through gases like oxygen, methane, and carbon dioxide, which are produced or modified by living organisms. Finding similar markers on other planets could provide the first tangible evidence that we are not alone. However, detecting biosignatures in the vastness of space is not a straightforward task, and scientists must rely on sophisticated techniques to identify potential signs of life in the atmospheres of distant exoplanets. Examples of biosignatures: oxygen and methane in atmosphere. As one of the most promising biosignatures is oxygen, especially in combination with methane. On Earth, oxygen is produced by photosynthesis, a process carried out by plants, algae, and cyanobacteria. The presence of oxygen in a planet's atmosphere suggests that photosynthetic organisms are actively producing this gas. Similarly, methane, which is often produced by microbes, plants, and animals on Earth, could indicate biological activity if detected in large quantities. On Earth, oxygen and methane are found together in a delicate balance that is constantly replenished by life. The simultaneous presence of oxygen and methane in an exoplanet's atmosphere would be considered a strong biosignature. However, this combination is difficult to maintain without a biological source, making it an exciting possibility for detecting life. While non-biological processes, such as volcanic activity or chemical reactions, can produce methane and oxygen separately, the combined presence in a planet's atmosphere would be unlikely without life playing a role. Seasonal changes indicating plant life. In addition to atmospheric gases, seasonal changes can also provide hints about life. On Earth, the changing seasons affect plant growth, influencing the composition of the atmosphere. For example, during spring and summer, plants absorb carbon dioxide and release oxygen, while in the fall and winter, this process slows down as plant life becomes dormant. If similar seasonal variations are observed on an exoplanet, it could indicate the presence of plant-like life forms that follow a cyclical growth pattern. While detecting seasonal changes on distant planets is challenging, it's not out of the realm of possibility. By monitoring a planet's atmosphere over time, scientists could look for variations in gases such as oxygen, carbon dioxide, and water vapor that correspond to seasonal patterns, providing indirect evidence of plant life or other forms of biological activity. Technologies used to detect biosignatures. One of the most effective ways to detect biosignatures on exoplanets is through spectroscopy. This technique involves analyzing the light from a star that has passed through or reflected off a planet's atmosphere. Different molecules absorb light at specific wavelengths, creating a unique spectral signature. By studying these signatures, scientists can identify the chemical composition of the planet's atmosphere and search for potential biosignatures. In particular, infrared spectroscopy has proven invaluable for detecting atmospheric gases. Telescopes like the James Webb Space Telescope, JWST, and the Hubble Space Telescope are equipped with spectrometers that can capture and analyze the light emitted or reflected by distant exoplanets. JWST, with its advanced infrared capabilities, will be able to study the atmospheres of exoplanets in unprecedented detail, helping to identify the chemical markers of life. For example, by analyzing the absorption spectra of starlight, scientists can detect the presence of oxygen, methane, and other gases in the atmospheres of exoplanets. When an exoplanet passes in front of its host star, some of the starlight filters through the planet's atmosphere, leaving behind a unique chemical signature. This transit spectroscopy allows astronomers to determine the composition of a planet's atmosphere, even if the planet itself is millions of light-years away. In the future, high-resolution spectrometers on next-generation telescopes will provide even more precise measurements, enabling the detection of subtle traces of biosignatures that were once thought to be beyond reach. Challenges in detecting biosignatures. While the search for biosignatures is an exciting and promising field, it is not without its challenges. One of the biggest hurdles is the possibility of false positives, situations in which the detected chemicals or patterns may seem to indicate biological activity, but in reality, have non-biological origins. For example, methane can be produced by geological processes, such as volcanic eruptions, or by the breakdown of organic matter in the absence of life. Oxygen, although a key biosignature on Earth, could also be produced by non-biological processes like the breakdown of water into hydrogen and oxygen by ultraviolet light. Therefore, detecting these gases alone is not enough to confirm the presence of life. Scientists must carefully rule out other possible explanations before making a definitive conclusion. Another challenge is the limitations of current technology. While telescopes like JWST will greatly enhance our ability to detect and analyze exoplanet atmospheres, the technology is still in its infancy when it comes to identifying biosignatures. Many exoplanets are located light-years away, and the signals from their atmospheres are faint and easily drowned out by the overwhelming light of their host stars. Detecting subtle traces of life-related gases requires advanced instruments, extremely sensitive detectors, and the ability to separate the signal from the noise. Moreover, atmospheric conditions on distant exoplanets could complicate biosignature detection. A thick, cloudy atmosphere or extreme temperatures could obscure the light passing through the atmosphere, making it difficult to obtain accurate readings. Additionally, many exoplanets orbit stars that are prone to flares or intense radiation, which could strip away their atmospheres or alter their chemical makeup, complicating the search for biosignatures. Looking ahead, the future of biosignature detection. And despite these challenges, the search for biosignatures continues to be one of the most promising aspects of exoplanet research. As technology advances, the ability to detect and interpret these signs of life will only improve. Future missions and telescopes, such as the Nancy Grace Roman Space Telescope, will provide further insights into exoplanet atmospheres and increase our chances of detecting biosignatures. The growing understanding of what constitutes a biosignature, coupled with advancements in observational technology, means that we are closer than ever to answering one of the most profound questions in science: is there life beyond Earth? As we continue to refine our methods of detecting biosignatures, the possibility of discovering life on distant exoplanets becomes increasingly real, transforming the search for life into one of the most exciting frontiers of modern science. Theoretical possibilities: could we live on an exoplanet? Colonization challenges: the distance barrier. The idea of humanity settling on an exoplanet is both fascinating and daunting. One of the greatest obstacles to this dream is the immense distances that separate us from these distant worlds. Even the closest known exoplanet, Proxima b, is 4.24 light-years away. To put this into perspective, the fastest spacecraft ever built, the Parker Solar Probe, travels at a maximum speed of about 430,000 miles per hour. At that speed, it would take over 6,000 years to reach Proxima b. Most other potentially habitable exoplanets are hundreds or even thousands of light-years away, making them unreachable with current propulsion technology. The vastness of space poses logistical challenges that are almost unimaginable. Even if we could develop spacecraft capable of traveling at a significant fraction of the speed of light, the journey would still take decades or centuries. This would require generation ships, self-sustaining spacecraft where entire communities of humans could live, reproduce, and die while traveling through the void of space. Such a project would be an unprecedented engineering feat and raise profound ethical and social questions. How do you ensure the survival of a society isolated for generations? What happens if something goes wrong on the way? Colonization challenges, planetary conditions. Even if we could solve the problem of distance, there's no guarantee that a potentially habitable exoplanet would actually be livable for humans. Many of the exoplanets identified in the habitable zone have conditions that might allow for liquid water, but that doesn't mean they're Earth-like. Gravity, for example, could pose significant challenges. A planet like LHS 1140b, with a mass nearly 7 times that of Earth, likely has much stronger gravity. Living in such an environment could strain the human body, making basic tasks incredibly difficult and potentially causing long-term health issues. The atmosphere of an exoplanet is another critical factor. While some planets may have atmospheres thick enough to support life, the composition of those atmospheres could be toxic to humans. High levels of carbon dioxide, sulfur dioxide, or other harmful gases could make survival impossible without protective suits or enclosed habitats. Additionally, the availability of natural resources, such as water, minerals, and energy sources, would determine whether a colony could be self-sustaining or perpetually reliant on supplies from Earth, a logistical nightmare given the distances involved. Terraforming, making an exoplanet habitable. If a planet isn't naturally suitable for human life, could we make it habitable? This is the concept behind terraforming, the idea of transforming an inhospitable planet into one that resembles Earth. While much of the focus on terraforming has centered on Mars, the same principles could theoretically be applied to exoplanets. Terraforming involves altering a planet's atmosphere, temperature, and surface to create conditions suitable for human life. For instance, scientists have proposed releasing greenhouse gases on Mars to warm the planet and create a thicker atmosphere. If similar processes could be applied to an exoplanet, they might create a breathable atmosphere and allow for liquid water to exist on the surface. However, the challenges are immense. Terraforming a planet would require technology and resources far beyond what we currently possess. The process could take centuries or even millennia, and there's no guarantee of success. Furthermore, ethical questions arise when considering such projects. If an exoplanet already harbors microbial life, would terraforming it be a form of ecological destruction? Would humanity have the right to alter an alien world to suit our needs? Faster than light travel, breaking the speed limit at the vast distances between Earth and exoplanets have led scientists and science fiction enthusiasts alike to explore the possibility of faster than light, FTL, travel. While current physics suggests that nothing can travel faster than the speed of light, some theoretical models offer potential workarounds. One concept is the warp drive, a technology popularized by science fiction. The idea involves bending or warping space-time to allow a spacecraft to effectively move faster than light without breaking the laws of physics. In theory, a warp drive would compress space-time in front of the ship and expand it behind, allowing the craft to surf on a wave of space-time. While promising, the concept remains highly speculative and would require exotic forms of energy, such as negative energy or dark matter, that are not yet understood or accessible. Another possibility is the use of wormholes, hypothetical tunnels in space-time that could connect two distant points in the universe. If wormholes exist and could be stabilized, they might allow for near-instantaneous travel between Earth and an exoplanet. However, like warp drives, wormholes remain purely theoretical, with significant scientific and engineering hurdles to overcome. These advanced propulsion concepts, while exciting, are unlikely to become reality in the near future. Developing such technologies would require a revolution in our understanding of physics, as well as immense resources and international cooperation. Still, the pursuit of FTL travel continues to inspire scientists and dreamers, offering a tantalizing glimpse of what might one day be possible. Controversial insights. Should we focus on saving Earth instead? The dream of colonizing an exoplanet often raises an uncomfortable question. Should we invest billions, or even trillions, of dollars searching for a backup planet when we could focus on preserving the one we already have? Earth is uniquely suited to life, and no exoplanet, no matter how habitable it appears, could ever replicate the intricate ecosystems and biodiversity that have evolved here over billions of years. Some argue that the resources spent on space exploration and exoplanet research could be better used addressing the urgent challenges facing Earth, such as climate change, deforestation, and pollution. They contend that the notion of finding another Earth may distract from the pressing need to make our planet more sustainable for future generations. On the other hand, Proponents of exoplanet colonization argue that exploring the universe and searching for habitable worlds are not mutually exclusive with solving Earth's problems. They point out that space exploration drives technological innovation, inspires global collaboration, and provides a long-term plan for the survival of humanity. After all, Earth's history includes numerous mass extinction events, some caused by external factors like asteroid impacts. Having a second home, even if it's far away, could safeguard humanity from existential threats. Ultimately, the debate underscores the complexity of humanity's relationship with space. The search for habitable exoplanets is as much about understanding our place in the universe as it is about survival. While it's vital to prioritize the health of our own planet, the pursuit of knowledge and the desire to explore are fundamental aspects of what it means to be human. The possibility of a new frontier. The idea of living on an exoplanet may seem like the stuff of science fiction, but it reflects humanity's unyielding curiosity and determination to explore the unknown. While the challenges are immense, ranging from the vast distances involved to the difficulty of creating livable conditions, the potential rewards are equally profound. Discovering a world where humans could thrive would redefine our understanding of life and open a new chapter in the story of human exploration. Yet, as we look to the stars, we must also look inward, recognizing the responsibility we have to care for the planet we call home. Whether or not we ever set foot on an exoplanet, the search for habitable worlds reminds us of the fragility and uniqueness of Earth, a reminder that may ultimately inspire us to protect it for generations to come. Are we alone? The existential question of another Earth, the discovery of another Earth, or even the realization that Earth is not unique, poses one of the most profound questions humanity has ever faced. Are we alone in the universe? This question is not just scientific but deeply existential, touching on the very core of what it means to be human. For centuries, humanity has gazed at the stars, wondering if life exists elsewhere. If we were to find a habitable exoplanet, or evidence of life on one, the implications would ripple through every aspect of society, from science to culture to individual perspectives on existence. The confirmation of another Earth-like world, especially one harboring life, would fundamentally shift our understanding of our place in the cosmos. It would force us to confront the possibility that we are not the central figures in the universe's story but merely one small chapter in a much larger narrative. Such a realization might unite humanity, encouraging global cooperation and a sense of shared destiny. Alternatively, it could provoke fear and uncertainty, as we grapple with the unknown implications of not being alone. Even the act of searching for another Earth speaks volumes about our nature. It reveals an inherent curiosity, a longing to connect with something greater than ourselves. The search for habitable exoplanets is not just about survival or scientific advancement. It's about addressing the deeply human need to understand our origins, our purpose, and whether life, perhaps even intelligent life, exists beyond the confines of our planet. Ownership and ethics. Who has the right to an exoplanet? As humanity ventures further into space, the question of ownership and ethics becomes increasingly relevant. If we were to discover a habitable exoplanet, who would have the right to claim it? Would it belong to the nation or organization that discovered it, or would it be considered the property of all humanity? These questions are not merely hypothetical, they are ethical dilemmas that demand thoughtful consideration. The history of colonization on Earth provides a cautionary tale. Many past explorations led to exploitation, displacement, and destruction, driven by the desire for power and resources. If we were to colonize an exoplanet, there is a risk that history could repeat itself, especially if such a planet harbors valuable resources or, even more significantly, life. Would we respect the intrinsic value of an alien ecosystem, or would we prioritize humanity's needs at its expense? International treaties, like the Outer Space Treaty of 1967, currently state that celestial bodies, including planets, are not subject to national appropriation. However, these agreements were drafted long before the serious possibility of exoplanet colonization arose. As technology advances, new frameworks will be needed to address the ethical and legal challenges of settling on another world. Should exoplanets be declared universal commons, protected for the benefit of all? Or would economic and political realities lead to competition and conflict over their control? The discovery of an exoplanet with life would complicate these questions even further. How do we balance humanity's needs with the rights of alien organisms? If such life forms are simple microbes, would it be ethical to terraform their planet, potentially destroying their ecosystem? The answers to these questions will shape humanity's legacy as we step into the role of interstellar explorers. Impact on religion and philosophy, shifting belief systems. The discovery of another Earth or extraterrestrial life would also have profound implications for religion and philosophy, challenging long-held beliefs and inspiring new ways of thinking about existence. For many religious traditions, humanity occupies a special place in the universe, often seen as the pinnacle of creation. The realization that life exists elsewhere, or that Earth is just one of many habitable planets, could force a re-evaluation of these beliefs. Some religious thinkers argue that the discovery of extraterrestrial life would not undermine their faith but expand their understanding of creation. If life exists on other planets, it could be seen as a testament to the vastness and creativity of a divine being. Others might struggle to reconcile their beliefs with the idea that humanity is not unique. Questions would arise: do extraterrestrial beings have souls? Are they part of the same spiritual plan as humanity, or do they represent a separate creation? These are not just theological debates but deeply personal questions that could influence how individuals view themselves and their place in the universe. Philosophy, too, would be profoundly affected. For centuries, philosophers have grappled with questions about the nature of existence, consciousness, and humanity's role in the cosmos. The discovery of another Earth, or intelligent life, would add a new dimension to these debates. What does it mean to be human if we are no longer alone? Would we see ourselves as part of a larger interstellar community, or would the vastness of life in the universe make us feel even smaller and more insignificant? At the same time, the search for habitable planets could inspire a renewed sense of purpose and unity. Philosophers might argue that the discovery of another Earth is a reminder of our shared humanity and the need to work together to protect both our planet and the broader cosmic ecosystem. It could also encourage new ethical frameworks for interacting with extraterrestrial life, emphasizing respect, humility, and the recognition of the interconnectedness of all living things. A new cosmic perspective. The philosophical and ethical implications of discovering another Earth extend far beyond science. They touch on the deepest aspects of human identity, culture, and morality. As we continue to search for habitable exoplanets, we must confront not only the technical challenges of exploration but also the profound questions it raises about who we are and what we value. Are we prepared to meet the responsibilities that come with discovering another world? Can we avoid the mistakes of our past and approach this new frontier with respect and foresight? And how will the knowledge that we are not alone, or that Earth is not unique, reshape our understanding of ourselves and our place in the cosmos? The search for another Earth is more than a scientific endeavor. It is a journey into the unknown, not just across space but within ourselves. It challenges us to think deeply about our relationships with each other, our planet, and the universe, offering a chance to redefine what it means to be human in the vast, interconnected web of existence. Summary of key points. The journey to uncover the mysteries of habitable exoplanets has brought us closer to understanding the universe and our place within it. From the discovery of promising candidates like Proxima b, Kepler 452b, and the fascinating TRAPPIST-1 system, to advancements in technology such as the James Webb Space Telescope and AI-powered data analysis, the search for another Earth has transformed from a distant dream to a tangible scientific endeavor. Yet, the challenges remain immense. The vast distances separating us from these planets, the technical limitations of current propulsion systems, and the unknown environmental conditions of these worlds present significant obstacles. Despite these hurdles, each discovery adds a new piece to the cosmic puzzle. We've learned that the universe is far more diverse and abundant than we ever imagined, with thousands of exoplanets already identified and potentially billions more waiting to be discovered. These findings underscore the incredible potential for life beyond Earth and the possibility of a second home for humanity, should we ever need one. Looking ahead, the future of exoplanet research. The next era of exoplanet research promises to be even more transformative, driven by rapid advancements in technology and international collaboration. The James Webb Space Telescope has already begun to revolutionize our understanding of exoplanet atmospheres, offering unprecedented insights into the chemical compositions and potential biosignatures. Future missions, such as the European Space Agency's Plato and NASA's Nancy Grace Roman Space Telescope, will expand the search for Earth-like planets around nearby stars and provide critical data about their habitability. Artificial intelligence will continue to play a pivotal role in processing vast datasets, identifying faint signals, and even simulating conditions on distant planets. Machine learning algorithms will refine their ability to detect smaller, more Earth-like exoplanets, bringing us closer to discovering true Earth analogs. I will also assist in analyzing atmospheric data, searching for markers of life such as oxygen, methane, and water vapor with greater precision than ever before. Looking further ahead, advancements in propulsion technology could eventually make interstellar travel a possibility. Concepts like solar sails, fusion drives, and even speculative ideas like warp drives and wormholes are being explored by scientists as potential solutions to the challenge of reaching distant worlds. While these technologies may still be decades or even centuries away, the dream of exploring and perhaps even colonizing an exoplanet remains a powerful motivator for innovation. Collaboration between space agencies, private companies, and international researchers will be key to overcoming the challenges of exoplanet exploration. Shared resources and expertise can accelerate the development of new telescopes, spacecraft, and analytical tools, ensuring that the search for another Earth remains a global effort. Final thought, a question for the future. The search for habitable exoplanets is as much a reflection of humanity's ingenuity as it is a testament to our enduring curiosity. It's a journey that challenges us to push the boundaries of what's possible and to imagine a future where life extends beyond the confines of Earth. But it also raises profound questions about our priorities, responsibilities, and aspirations. If there is another Earth out there, a world with oceans, mountains, and perhaps even life, what would we do differently this time? Would we treat it with the respect and care that our own planet so desperately needs? Would we use the lessons of our history to create a more harmonious relationship with the environment and each other? Or would we repeat the mistakes of the past, bringing with us the same conflicts and challenges that threaten our planet today? The search for another Earth is not just about survival, it's about reimagining what it means to be human. As we look to the stars, let us not forget the unique beauty of the planet we already call home. For in our quest to find another world, we are reminded of just how precious our own truly is. The answers we seek may lie among the stars, but the choices we make here on Earth will shape the legacy we leave behind.